Thank you very much. It's a pleasure to be here today and to be the first speaker to open this event, this Energy System Week. Since I'm the first speaker, I allow myself to be quite general and give an overview of a few problems. I think there will be quite a few more talks that will be more technical. So I will not get into too much detail, but if you have any question, we can discuss it afterwards. Through my education, I've been more of an optimization guy, say up to my master degree. And afterwards, I got into forecasting through my PhD and my research since then. So, and now as I see it, one of the key aspects of integrating renewables is to optimally merge the two in order to make optimal decisions for the management of these systems, energy systems. I'm a professor at the Technical University of Denmark. Even though I was educated as a mathematician, my professorship is in the electrical engineering department. And actually it's quite nice. It gives the possibility to merge different type of expertise. I have to acknowledge input from these guys, at least, at the very least. These were in my group at the Applied Maths department, and some are in connected groups in Copenhagen or also at DTU. So a lot of the material there is actually not from me, it's also from them. The context, I think you know the context, but these figures were released, I think, 2 weeks ago, so it's my pleasure just to show them. We have quite a lot of wind power installed all around Europe. Some of the leading countries historically would be Denmark, Germany, and Spain. But if you could see the figures, you will see them when you have the PDF of the presentation. There are new big players on this map, and UK is one of them. UK has decided to invest massively offshore, which is, I think, a general trend. Through the trend before Germany, Spain, and others was to have a lot of onshore wind energy. Onshore and offshore, there's a lot of differences in terms of methodology, but also in terms of how to integrate the power generated from this wind farm. If you consider two key challenges, is that the first one would be that you concentrate a lot of power generating facilities offshore. So all these problems we're going to discuss, viability, predictability, and so on, you cannot hope you will ever have a smoothing effect that will kind of help you. You concentrate everything, you're going to get maximum trouble. The other thing is that if you put a lot of these wind farms here, for instance in the North Sea, the regulatory framework is not very clear. I mean, you're going to connect the wind farms to different countries with different markets, different ways of operating, maybe different grid codes. So what rules are you going to follow? What kind of value your energy is going to have since you're connected to different markets? How is it going to evolve? Is this going to become one market zone with only zero cost power and no load? What's going to happen? That's one of the key questions. There's a lot of other problems, but when we see the development of wind power in Europe right now, I think these are two of the major ones. I would like to discuss why and how this stochastic power generation is impacting electricity markets. I would like to talk of electricity markets instead of power system operation per se, because the markets directly show what the real big picture is. Then I want to discuss some empirical investigation results to show you that this is already happening today. We saw that quite a lot in Scandinavia, this impact of wind on markets. Then I will go through all these decision-making problems and the role of forecasting, what type of forecasts are used, how they can be optimally or suboptimally used. And finally, I will look at the future and how we feel we could and should better accommodate stochastic power production through the market. And finally, outlook, to give my opinion on where we're going. So why and how this stochastic power generation impact the market? Most of you know how the electricity market works, but some of you don't. So I would like to give you a little rapid overview. The traditional electricity market, say, has a day-ahead market where you place offers, consumption, and production. And then there's a market clearing mechanism that decides on the optimal quantity to be produced and consumed for the following day. So let's say in Scandinavia, the market is cleared at 12 at noon for the following day between midnight and midnight. Obviously, if you participate in this market with wind power generation, to place offers, then you need to kind of guess what you're going to produce. And there are different ways of guessing, and it can cost you money to make a wrong guess. So you have to be careful with that. Then there's this intraday markets that are not so much used actually so far in Scandinavia, but that gives potential for corrections during the day. And finally, there's the balancing market that's near real time, and that permits to correct for the differences that are observed between the day-ahead plan that came out of this day-ahead market and what's really happening in near real time. This is to be seen as some kind of penalization for those who deviate from their original contract in the spot markets. Because obviously, if you deviate from your original contract, you're going to have to pay to put the system back to balance, plus an extra penalty for having put the system off balance. In general, these kind of markets are really not nice for wind power producers. And even though in Scandinavia the financial penalties are not so high, it is on average quite penalizing, more maybe in the Netherlands and in Germany. And in the future, there's more and more wind, and the problems are becoming more and more stringent. There are going to be more and more penalties for these wind power producers. One of the key effects that makes the impact of wind on electricity market is this merit order effect. The way the supply offers are ranked is depending on their short-run marginal cost. And so you typically have this kind of curve here, the supply curve, the global supply curve with the market, and then you would have, this is a real caricature, a demand curve with a little elasticity. Where these two curves meet, you get the quantity and the price for this time units in the market. So typically an hour for the following day. Wind enters at the very left of this supply curve because it has close to zero short-run marginal cost. It can actually be negative if you have subsidies. And then wind, with its variability and lack of predictability, is just pushing this curve left and right, depending on how the wind blows. So if it pushed the curve on the right, you can see it changed the point here, the crossing point from here to here. If there's less wind than this average here, the point jumps there. So you can actually affect the price just because of how much you think the wind is going to blow during this time unit. That's the basic concept. So what we say is that we consider wind is a stochastic driver for electricity market price and quantities. I was mentioning viability and predictability of wind power production. We have very nice test cases in Denmark. We had the first large offshore wind farm at Hornsrev on the west coast of Denmark. It's been operating for more than 10 years now. And I've been lucky enough to have access to this data. The data are wind speed, wind direction, power generation for every turbine, 1 Hertz in terms of frequency. So you can do a lot of things with this data. But one of the nicest things to do with this data is just to plot them and illustrate the problem. I'm not sure of how much you've seen offshore wind data. This is, for instance, an episode of 5 days with 10 minutes wind speed measurements. And you can see you have some kind of lower frequency cycle, say, but then you could have also some wild fluctuation where wind is just jumping from 10 minutes to the next. And in terms of power generation, power is a conversion of wind through the power curve of the turbines. You then have, I would say, a magnifying effect. So the fluctuations in wind can be of higher amplitude through conversion through the power curve, or it can be also bounding the fluctuation, because when you reach nominal capacity, it's just flat, the power output of the turbines. But you can see this is a real event, this kind of drop in power with another jump and then another drop. Then our TSO, our transmission system operator in Denmark, has to deal with this kind of event. It's really, really costly, and it's really problematic for them. So this is the question of viability of wind power production. And then the second part of the problem is to try to predict that. And I can tell you, trying to predict this kind of jumps in the wind speed or in power production, it's almost mission impossible. We can try to do something, but to predict accurately is very difficult. I was mentioning the power curve of a wind turbine, but you can see also a power curve of a wind farm, power curve of a portfolio that just spread geographically. That would be some kind of caricature power curve. And the problem with this power curve is that even if wind speed or wind in general was something that would be nicely Gaussian and linear, whatever happens, when it would get converted through the power curve, it wouldn't be Gaussian and linear anymore. So by nature, we have to deal with a process that is double bounded between the nominal capacity of the wind farm and zero, obviously, and it's also nonlinear due to the effect of these bonds. Already, just in terms of time series modeling, there's quite a few challenges with this nature of the process. There are quite a few papers on that. They are quite rare, but I could indicate papers if you're interested. Then empirical investigation. I had a student, was that 5 years ago. His job was to collect all the data from the Scandinavian Nord Pool and try to find out how much we can characterize the effect of wind power, and mainly the forecast, on the market. I was showing you before this curve, this global supply curve. What's going to push this point left or right? It's not what the wind is actually doing, since you're placing your bids 12 to 37 hours in advance. It's what you think the wind is going to do tomorrow. So who's having an impact on the market? Not the actual wind power generation. It's your forecast of the wind power generation. So instead of the more classical econometrical analysis that were done before, Tryggvi is from Iceland, so that's why he has his name. Tryggvi has looked at the data, but the input, the explanatory variable that would explain what's going on with the price is the wind power forecast. And more precisely, the wind power penetration forecast. So how much of the wind is going to be used to meet the electricity consumption. That's one of the main plots from this analysis. It's been published in Energy Economics since then. You have here the hour of the day. You have here the wind power penetration between 0 and 1. 0, no wind predicted for tomorrow. 1, you predict that 100% of your consumption is going to be met by wind power generation. While here the maximum in this plot is what, 65, I think, percent. We managed to reach 100% and more. It's quite rare, obviously, but still we managed. On average, last year we had 30% penetration. So you can see on this plot, if there's no wind, we can recognize a classical pattern, impact of the hour of the day on the mean price for electricity in the day-ahead market. This is due, obviously, to quantities. But then, as we think wind is going to blow, there is a real downward pressure. And actually, from this curve to the curve there, when there's a lot of wind that's thought to blow tomorrow, there's a decrease by 50% average in the price. So that's a tremendous effect. And if you want to read more, you can get this paper in Energy Economics. It's not only an effect on the mean price, obviously. The mean is just one summary characteristics of the distribution of prices. So Tryggvi looked a bit more into this distribution of prices. And what we could see, just to summarize rapidly, is that extreme prices, you may notice sometimes, if you think wind is going to blow tomorrow, all these extreme prices disappear. And you might think, well, it's a good thing. But maybe some of the units, they count on these high prices that are quite rare, but we know they're going to happen, to recover their cost. But no, wind, you see wind blowing between 0.5% to 40, 100%. You have here the distribution of prices. The prices are all pushed towards the left, so towards lower values. The extreme prices disappear. And what happens is that 0 or even negative prices, now that it's allowed in Scandinavia, they appear. So there was an event again around Christmas this year where prices were negative for quite a long period of time. And this is also, some engineers would say, well, it cannot be possible. Economists would tell you, actually, it makes sense. But at the end of the day, the units that participate in this market, they're having problems with this negative prices situation. This situation was 4 or 5 years ago. There's going to be more and more wind. If we don't change the market design, there's going to be more and more 0 and negative prices. And there's never, almost never going to be these high prices anymore for certain units to recover their cost. This has to be remembered. Then let's get to decision making and forecasting. That would be what we need to discuss over the week, besides this contextual problem. There's a lot of very interesting decision making problems. If you're a mathematician, you can pick one of these problems, and I'm sure there's a lot of great things to do. If you consider the system as a whole, we need to define some reserve requirements. So it's backup capacity somehow in case, to make it short. Then there's the problem of unit commitment and economic dispatch. So what types of units should be on for the following period, and how we use the system in the most economical manner. Then for those who have the chance that they can combine wind and hydro, there would be some kind of optimal operation strategy. You could consider also optimal offering strategies in the market. There's obviously similarly a generalization with storage. That can be any type of storage, chemical or hydro or other things. And then we can get more to the market aspects, which are core to my interests, with the design of optimal trading strategies in this market. That's a very thrilling research area. And then the other side of it is market clearing and market design more generally, how we can change the market and make it more appropriate for the situation with a lot of renewable power generation in there. For all these decision-making problems, you need forecast as input because of the time scale involved and because you want to have to make some optimal decisions. There's a lot of forecasts that can be used, and I'm going to go through them in a minute. The classical type of forecast is the deterministic forecast. And most of the forecast users, they love that. They just want deterministic forecasts. It's just safe, you know what's going to happen. There's one possibility only. There's no uncertainty officially. Obviously, there'll be a forecast errors, but let's forget about it. And these deterministic forecasts are the easiest to integrate into these decision-making processes. Then quite a few researchers have been pushing for probabilistic forecasts, and I will describe them a little bit afterwards. Probabilistic forecasts are somehow the optimal input to all these decision-making problems in one form or another. Then there is risk indices. If you come from France or some other countries that show on TV the weather forecast for a few days ahead, you might have seen some risk indices. They tell you how much you should trust the weather forecast for 4 days ahead. So these kind of risk indices exist also for renewable power generation forecast. In my opinion, it's more for broad audience application, but some people argue they can also be used in decision making for making optimal decisions. I was mentioning decision-making processes. You can look at that also in terms of time scales. You could also look at that in terms of spatial scales, depending on the time scales, actually. For all these time scales, there are different types of problems that can be control, that can be scheduling, trading, maintenance planning, or more related to planning and investment. That goes from seconds to years. Some of us here might be more interested in this second to minute problems, some others in months to years. Whatever the scales, the issues are the same. Wind power generation, to name only this one, the other renewables have the same properties. This is a non-linear process. Even though if you look, I have to say this is challenged a bit. If you look at the very short time scales, if you make some assumptions that you're dealing with a linear process, it could still be quite okay. It is non-stationary for all these timescales, and I believe also we might not all agree on this statement. I believe it is non-stationary, but it could be local stationary, say. And then for most of these decision-making problems, the loss function, the cost function of the decision maker will be asymmetrics, complex, and non-stationary. So in this kind of situation, if you want the decision makers to make optimal decisions, you need to provide them with the full probabilistic forecast, I believe. These are examples, actually, of loss functions. I'm not going to go into detail with that, but typically, a forecaster who is trying to minimize root mean square error has this kind of loss function. So it's just a quadratic function. A trader that would trade wind power only would have this piecewise linear asymmetric cost function. On the two sides, the slope of the curve on the two slides, the slope of the two lines here are related to the penalties in the market for being long or short. And finally, if you're a portfolio manager or a system operator, you might have a more complex loss function. In all cases, the optimal forecast is a complex function of some of the probabilistic predictions you may use as input. Never it can be the deterministic forecast that you would get traditionally as input to decision making. However, this point forecast or deterministic forecast, they are the traditional input, as I said several times already. And just to give you a rapid example, for the leads forecast range of 2 days ahead, 2 days ahead that's used in the market, the forecasts are typically with hourly resolution here. This is the red curve, the forecast, and gives you the conditional expectation for every time unit in the future. So this is just the mean of whatever could happen. Here it looks nice when you get the measurements a posteriori. It could be a conditional expectation. It seems that we nicely captured the characteristics of the process. But in general, we really have no clue of how much the actual observation would deviate from this conditional expectation information. Predicting the mean of whatever can happen is just the mean. It can still go all over the place around the mean. So there's no way you can make optimal decision with that. And this is why some groups in Europe and in the US have worked quite heavily on probabilistic forecasting. And I think today, it's been 10 years, I think today we have quite a lot of knowledge and material for this forecast to be routinely produced. Actually, some of the methods I proposed were implemented in some forecasting software, and they're used for, I think, the whole Australia and in Canada. So these probabilistic forecasts are issued in practice, and they are hopefully used a little bit. Typically, the forecasts, there are predictive densities, so they inform about the predictive CDF for each lead time in the future. And this is a typical representation coming from Ken Wallace in the UK. So it just shows some central prediction intervals with increasing coverage rates. That's just a classical way to display this information. There's a lot of methods that are available today, and I think some of you might work on other methods, and there are new players coming in the field to propose a new approach. One of the issue with this forecast, 5 years ago, 10 years ago, people would tell you this is really the key, this is what you need for optimal decision making. Today we know it's still not enough for a lot of the decision making problem. Because these forecasts, since they inform on the predictive CDF for each lead time individually and each location individually, you're missing the interdependent structure. So you don't know how your potential forecast errors might be interrelated. And you might think, wow, that doesn't make much of a difference, but actually it does. If you were, these are based on probabilistic forecasts like this one, but I try to make some trajectories, temporal trajectories, to find out what could be the evolution of wind power generation in the future. Here, these trajectories are within the envelope of my probabilistic forecast, but I just consider there's no temporal interdependence. There's no correlation in time. So you have some kind of white noise wandering within this envelope. This doesn't really look like the kind of structure we have in the observation for this period. But if you are clever enough, say, or if you have some appropriate tools to model this serial correlation, then you can actually issue trajectories that can mimic the temporal structure that you expect for your process. There are ways to directly show the value of considering correlation instead of having this kind of white noise picture. That's the wind storage management. Typically, storage is used to compensate for the forecast errors. So if you don't consider the temporal correlation, the way you're going to operate your wind storage system is really going to be suboptimal. If you have this kind of observation of information about the interdependent structure, then you can design some optimal strategies for controlling and for operating your wind storage. I wanted to show you quickly some illustration for a real-world test case. That's my playground, Western Denmark. This is since, for these forecasting concepts, I would like to show what it looks like on a real test case, not just picking some bits and pieces on various examples. We've had the chance to get a lot of data from our transmission system operators over the last, 7 years, I think. And these data are for all the trafo stations where the wind turbines are connected. I think in the original data set we have 500 points in space and 7 years in time, with an availability that's quite amazing. For the trafo stations that are good ones, you have an availability of 99.7%, something like that, of the data. So these are real data sets where you can do something interesting. The way the system is operated is that you have 15 control areas. So somehow the transmission system operator is mainly interested in having forecasts for these 15 zones. And then for illustration, I have even aggregated even more so that we have only 5 zones, 1 to 5, which is north, west, east, southwest, southeast. And yeah, they have different share of the total capacity, but it's just for simplification. There is here 2.5 gigawatts of wind power installed, which might not sound too much for you in the UK, but for Denmark it means that this can go above, beyond the 100% penetration. And then we need to export to Norway or to Germany. So these are our point forecasts for the 5 zones. And what I wanted to illustrate by using this real-world test case is that for a small country like Denmark, if you look at the observations that are these little dots, zone 1, 2, 3, 4, 5, there is really a pattern that's similar when you look at different locations in space. This is because we have a single wind climate. Denmark is so small and flat that, I mean, it's pretty easy to imagine that the patterns are going to be quite similar at the different zones. Though there are little differences, you can see in the magnitude of the ramps up and down, in the timing of the draw. So these are aspects that need a little attention. When you make probabilistic forecasts, it's a bit of the same. There are events that are quite common for all the zones, even though they vary in terms of timing of the ramps and magnitude. But we can see also that uncertainty around the conditional expectation can vary in space and in time quite a bit. This assumption of uncertainty linearly increasing with the lead time is not valid for wind power generation. I was mentioning nonlinear double bonded process. That's one thing. But there's also the input uncertainty from the weather forecast that we have to remember. So somehow the uncertainty can grow and then decrease again and then grow again. That happens quite a lot. And finally, we have these kind of trajectories that have been used quite a bit in different studies for Western Denmark. And these are typically the type of scenarios that we issue that have interdependent structure in time and in space. There are quite a few methods that have been proposed for that. And one of the key challenges when you have this kind of forecast, space-time trajectories, is how to verify them. This is a real mathematical challenge, and if some of you want to look at that, I would be very happy. Then we get to accommodating this power generation in or through markets. One of the key aspects when you get this wind power in the markets is to clear the markets to put the power system in a state where it can operate optimally. The way we clear the market today with what we call the conventional market clearing procedure, it's totally disregarding the characteristics of renewable energy, meaning variability, stochasticity, and limited predictability. So we had the chance that our Strategic Research Council in Denmark decided to found a project that started just a few weeks ago. We'll try to find out how we can actually design markets that could better integrate renewable energy. And for us, it's really wind that's in question here. We have a nice set of partners, economists for the business school, mathematician from Copenhagen University, DTU, that's me and some colleagues from the Applied Maths department, the energy interest organization in Denmark, the transmission system operator, and then some partners from abroad. You might know Stein Erik Fletten and Antonio Conejo, who I think are quite known for their work on electricity markets and stochastic optimization. We're also advised by some nice international collaborators who would tell us if what we're doing could actually be taken abroad. That's one of the fears somehow when Denmark invests in projects, that we're just focusing on our little country and our own situation, and that after you cannot really export the concept. So yeah, there'll be a web page soon for this project if you're interested. It just started, so it's not up yet. The vision is that we'll propose some new approach to market design, and the two things in question are really how you get the wind power generation or stochastic power generation in a better way, and how also you allow for a more proactive role of the demand. The ultimate goal is to actually verify that we create a more healthy environment for investment. So you can go in detail when you look at the PDF. I'm not going to explain all the aspects of the project. One of the things I would like to illustrate, though, we've done this work based on some toy models, and that's one of the points I discussed in my abstract. Already the market procedure we use, already today the market clearing procedures we use, they are not appropriate for having so much wind power in the system. And so what we've been doing is that we've been looking at some conventional way of clearing the market, and we've put it in parallel with the stochastic optimization way. It's Geoffrey Pritchard and Andy Philpott from New Zealand that published a paper 2 years ago, I think, in Operation Research, explaining that if you build an energy-only market with a nice stochastic optimization setup, then you would get the most of it. And somehow their proposal is nice, but it goes against some of the basic economic, I would say, properties you want to have for your market. So somehow we have several schools of thought that are the conventional ones and the more advanced stochastic optimization based ones, and we have to find an in-between. I will illustrate for you afterwards. This is clearly going to fail soon as we have more and more wind power in the system. This is clearly the optimum way to go, but it cannot be applied in practice because of reluctance of system operators and some basic economic issues. So we have to find ways, and the two, I think, key paths that are mentioned today is how to clear the market in a conventional setup, but with some improved dispatch of stochastic production. So I will explain that in a little bit. And then the other way would be to use robust optimization. So you just try to clear your market and trying to protect yourself against the worst case scenario. That's nice. That has nice properties because it scales up quite easily. While all these stochastic optimization algorithms that are proposed by Pritchard, for instance, they don't scale up nicely as the size of the system increase and increase. But these are current research problems. It's not like I'm coming here to give you some truths or show you some practical results. These are real research problems, and only toy model results exist. For illustrating my point, we've done some work. It's a paper by Juanmi Morales, a colleague, and others, including me, that's under review. We looked at a system that's been used by quite a few for discussing this stochastic unique commitment and market clearing ideas. It's a 24-bus system, the IEEE RTS. The characteristics are given in this publication. And it has 2 giga of demand and value type of generator. There's nuclear, there's hydro, all the fuel costs are realistic. And then we have wind in this system. I've put only 2 wind farms there, and we vary the penetration of the wind and the correlation in space for these wind farms. We look at energy-only market clearing, so that's a setup we believe is important for the future. And then there's comparison of the conventional market clearing. So the way it is today in Scandinavia and the Nord Pool, we really apply their procedure. We've put the stochastic optimization procedure of Pritchard and Philpott, and then a procedure that we propose, which is to use the conventional market clearing, but to try to be smart and have an optimal dispatch of wind power generation. I will explain what it is in the outlook in a few minutes. We have compared for 2 correlation in space for the wind power generation, and as a function of the wind power penetration, we've looked at the expected cost of power system operation. So that's adding the dayhead and the balancing cost in terms of energy. This curve here with the little stars, that's the conventional market clearing. And as you can see, the costs are decreasing, decreasing, decreasing with wind power penetration. Obviously, you're capturing the nice effects of having more wind in the system, but then you're reaching a breaking point. And I'm not going to say this is the breaking point for our markets today, but here in this setup, the breaking point would be around, I don't know, 37% penetration. Then from this point, the costs are going to increase. And as you have more correlation, especially for your wind, the effect would be getting worse. And that's one of the key motivation of the work of Pritchard and Philpott, is to say, well, actually, we could conjecture there is this breaking point. If we have a stochastic optimization setup, we can actually ensure that this expected cost always decrease. Obviously, they're going to asymptote somewhere, but at least you have this nice property that you would always get something more as wind power penetration increase. As I was telling you, this cannot be implemented in practice as of today because you cannot ensure that the participating unit will recover their cost, whatever happens. So some people could participate in the market in a position where they know they're going to lose money, and this is not acceptable. So in this other last proposal, which is conventional market clearing but with improved dispatch, what you do is that you ensure they can recover the cost, whatever happens, and you also ensure that you get this nice property of the stochastic optimization framework that you always get a bit more as wind power penetration increase. You obviously deviate a little bit from this overall optimum because you have extra constraints with ensuring this cost recovery. But still, this proposal could be practical, and it has the benefits of the stochastic optimization framework. So I'm not trying to sell any procedure here. I'm just saying we have to find somewhere in between the conventional market clearing and the full stochastic optimization setup that can permit to have this kind of curve here. So my outlook, we have to accept the characteristics of stochastic power generation. If we want to have more and more, as is the case in the UK, as we are doing in Scandinavia, we have to accept all these things that are drivers of the electricity market and ultimately power system operations. These are the variability. Variability has a cost that might be much higher than predictability, actually. There's this limited predictability, and I also mentioned this idea of space-time correlation. Space-time correlation has a clear role to play, and it's quite complex. We need probabilistic forecast and stochastic optimization. In my opinion, they are key contributors to the way we're going to optimally operate the system in the future. But I was mentioning there's a lot of issues with that. A lot of issues are within, I would say, the gap between academia and the real world, say, because we can propose a lot of nice stochastic optimization idea and nice probabilistic forecasting approach, but the people who are operating the system in practice will not use them because they are scared, because they see issues to use that, or just because they don't want to see the uncertainty in there. So I think it's our role to educate them and to work with them so that we can find the, I'll say the best way in between. Market design, I believe, is one of the key because all the power systems are today operated in a market framework, and if the market doesn't operate in a way that's satisfactory for everybody, we're going to have some very nice conventional generators that are important for power system operation that are going to disappear. It has happened recently again in Denmark for us. 2 large power plants decided to just shut down because it was not really, I'd say, economical for them anymore to run these plants. But the transmission system operators say we need them. But in the framework, the market we have today, there is no price signals that make they want to stay there. There's no money coming back that makes they feel it's a good investment to have them running still. So how we design the market or change operational practices so that we can have this system working in a way that is economical, that's a real challenge. And so if this week of discussion permit to have economists, mathematicians, power system engineers, methodologists together to discuss that, I believe it's a good thing. So thank you.
Yeah, thank you very much for that very nice overview of the whole raft of challenging problems.
Yeah.
Got time for a quick question before we have coffee. Bear in mind also we have got a lot of time scheduled for discussion later in the week.
And so in the stochastic planning tool you were using, do you use trajectories to for the forecasts? And I was wondering how many trajectories would you need on average to grasp the uncertainty appropriately, which is there?
Well, that's a key issue. I didn't want to get into that. I don't know how much I can talk. Here the tools are all based on trajectories. If you want to consider multiple periods market clearing, so you need trajectories. The number of trajectories, if you consider this stochastic optimization framework, you cannot use that many trajectories because it gets so costly. In this kind of frame, this improved dispatch, I was saying, in a conventional market clearing framework, it's also the way it is programmed today. It's a bi-level programming. It's also very costly, so you cannot use many scenarios in practice. And that's a key challenge, because if you have very few scenarios, how good are you at representing actually the stochastics in the process? My opinion is that we are quite bad today. And we had a real-world demonstration actually in Ireland with Peter Maibaum, who developed a stochastic unique commitment. And in theory, we would have very nice benefits, but when we implemented it in practice for stochastic unique commitment for the whole island, the benefits were of only 0.7%, I think. While on paper, you can show some improvement of 25% maybe. So where does that come from? Was that I provided the trajectories? Was that my trajectories that were bad? Was that the fact that we could only use, I forgot, like 12, I think, as input to the stochastic optimization? Was that the units were badly represented? I don't know, but at the end, in practice, the benefits are not always there. And it might be because of this number of trajectories.
Chris, very quickly.
Yeah, may not be a short answer, but one question that Stan and I have discussed with National Grid on a number of occasions is how to assess the quality of probabilistic forecasts. Do you have any comments on how, in your work, you have produced metrics for the quality of different probabilistic forecasts?
It's actually my key expertise. That's my core interest. I don't have anything in there. But let me tell you, for point forecast, we've already published some standard framework with a lot of benchmarking available that can tell how good forecasts are depending on different things. And I think it's pretty well accepted. It was published 10 years ago. For probabilistic forecasts in the form of predictive densities, we know today what are the key properties and how to evaluate them. And I think I could give you a rough picture during the week of how it is done, and I mean, we know pretty much how good that is for having a clear view of the quality of probabilistic forecast. Then how does that translate to the value of the forecast when they're using decision making? That's another question. There's still a lot of research on that. But then I was mentioning, when it comes to the space-time trajectories, I've been publishing, I think, last year a paper on that, where, I mean, I was showing, and people at ECMWF, for instance, meteorologists also know that, for the ensemble forecast, it's just nearly impossible to evaluate these trajectories. The dimension is just so high, and the samples are so small. How do you do it? So we have, for this type of forecast, we have some clues, but there's no accepted framework for evaluation. And that's a problem, because these are the kind of forecasts we want to use as input, and we have no clue of how good they are today. Well, not no clue, but...
Okay, so let's talk further.
Yeah, we can discuss that further.
Okay, there's more time for discussion later, tomorrow and subsequently, and we'll come back to all of these, I'm sure. Again, we'll stop for 10-minute coffee break. Again, Pierre, thank you very much indeed. Very, very interesting.